Yeah, g'day, it's Charlie ZL2CTM. Well, I've got half a day or so before family arrived to start Christmas, so I spent last night doing some design work and then this morning soldering up a pre-driver for the power amplifier. So I think I will look at some kind of FET for the power amplifier, but I just want to have a bit of a drive here to put out, in the region of say half a watt to drive that. So anyways, that's what we'll look at today, and we'll go from there. So let me just pan the camera back. So the circuit there is again just a two-stage amplifier using two N3053s in a Class A configuration for both. Three transformers, one matching the 50 ohm load into what will be the input resistance for this particular stage, a coupling capacitor transformer T2 looking at the load to the input to stage 2, and then a second one on the or a third one I should say on its collector matching what will eventually be the input to the power amplifier, which will be the FET, and like I say, in the region of half a watt. So a couple of specs then from the spec sheet. The 2N3053 500 so again 100 megahertz for the transition frequency, and a beta DC for the type of biasing current I'm looking at ranges between 50 and 250, so it gives me a geometric mean of 111, which I'll be using. And later on beta AC, so that transition frequency divided by 7 megahertz comes out at 14.3. Down here for the T2 up here, I was looking at the idea of using a match there, an L match. As you'll see later on in the actual circuit itself, I initially played around with that and didn't have too much success, so I've gone back to a traditional transformer. But it was more just having a bit of a play around with that. In terms of gain, I've got coming out of the balanced modulator and then through the final mixer, which will then drive will be the input to this particular stage, around half a milliwatt roughly. So if I want to get in the region of half a watt, then I'm looking at 10 log power out over power in the region of 30 dB. So if I can get say 2 lots of 15, which will give me a little bit of stability without going too crazy, that shouldn't be too far off. So that's what I'm going to be aiming for, 15 dB per stage. Now, like I said many times, this is not a tutorial. I'm actually quite keen to get input from people to see if this was an appropriate approach. My thinking in terms of approaching this amplifier here was to look at working from the back half here, moving to the front, looking at stage 2 for a start. If I want to generate half a watt, what does this need to look like? And then having said this is going to be a 15 dB stage, then what would I need to provide in terms of power input, which of course then would be the power out of stage 1. So this is the approach I've taken. I think the logic is about right from looking at EMRFD and the solid state design for the radio amateur. But like I say, if I've got something fundamentally wrong, please sing out, because again, these are not tutorials, this is just a video log of what I'm playing around with and what my thinking is in regards to this approach. So commit this to memory. So like I say, second half is stage 2, so therefore I've prefixed all the resistors with a 2, so R21, R22, R2E for the emitter resistor, R2X for the degeneration resistor. Over on the stage 1, same sort of logic, R11, R12, R1E, R1X. So they'll come important later on when we go over the page for the maths, what those designations are. Right, so so let's start off with stage 2. Now I don't have any script for this, so it's just me sort of talking out loud, so hopefully I don't sort of lose track of what I'm trying to say. Looks like everything's still in focus, which is good. Right, so in terms of a Class A amplifier, if I want stage 2 to output half a watt, I need to be cognizant that I'm only going to have, according to SSDRA, only about 30% efficiency for this particular amplifier. So I need to make sure that I'm providing from DC power from the power supply sufficient power to overcome the losses to generate as an aim point that's sort of half a watt. So initially you'll see a lot that a class amplifier is 50% efficiency, but that really is best case, and like I say, SSDRA talks about a figure of 30%. So if that's the case, then my half a watt out divided by 30% efficiency comes out 1.66 watts in. So I need to make sure that I'm providing this particular stage with 1.66 watts. And I also need to make sure that my my device, the 3053 transistor, can dissipate that power, which it can. It's a 5 watt device, and with the heatsink I've got, it's just fine. So having said that, for a 12 volt supply then, we know that power equals volts times current, so I can rearrange the formula to derive what my current needs to be going into it. So 1.66 watts, which we had up here, divided by 12 volts gives me a current of 138 milliamps. I'm not going to derate that any further because I'm already working out at roughly 30%. So that'll be my design quiescent DC current going into this particular stage, 138 milliamps. Also from SSDRA and the like, my desired load that I need to present to the collector in this particular stage for the bypass emitter, albeit with a small amount of degeneration, is VCC minus VE, sorry it's not very clear there, squared divided by 2 times my power out. Now I'm going to have the emitter set at the standard 1.2 volts that I'm using, so 12 minus 1.2 all squared divided by 2 times half a watt comes out at 116.6 ohms. So that's what I need to, with that T3 transformer, that very final transformer, to match that desired resistance with that, whatever I'm going to be hanging off, which will be that FET load, and I'll talk more about that later on. Rightio, so normal sort of maths that we've seen before. If my emitter is sitting at 1.2 volts and I've got 138 milliamps passing through it, that comes out of an emitter resistor for number 2, second stage, so 2E of 8.69, so standard value 8.2 ohms. For the voltage divider biasing, for the bottom resistor, so the R22, again as we've seen many times before, that 1.2 volts at the emitter plus 0.7 for the junction divided by 10 times our base current. So we'll assume that our emitter current is close enough to our collector current, so 138 milliamps divided by our beta DC that we worked out to be 111 comes out 152.8, so I'm going to use 150 ohms. The second resistor in that voltage divider biasing, so the upper resistor, so R21, will be 12 volts minus the voltage at the base, divided by now with the additional base current coming out of that stage there. The additional current going through that resistor comes out to 11 times our base current, or 738 ohms, so close enough. I use 680. Could have gone up to 820, but I've decided to go slightly down to 680 at this stage. Right, so again, if my logic is wrong here, please sing out. But now my gain for this particular amplifier is approximately equal to 10 log the load resistance divided by what I've called RE dash, which is the effective resistance of the collector circuit here, which is going to be R2E, the emitter resistor, in parallel with R2X. That 100 nanofarad capacitor there is required for DC blocking. So from a DC point of view, all the currents passing through here, which we saw before, 1.2 volts divided by our collector current establishes that. No current passing through here. But from an AC point of view, that's now a short, and these two are in parallel. So RE dash is R2E in parallel with R2X. So having said that, if I want this stage to be 15 dB, which I mentioned before, I can now rearrange this formula to work out what RE dash would need to be given that our RL, which we established up here, to be 116.6 ohms. So rearranging the formula, so take the 10 across to this side, we raise each side of the 10, and like I say, move that across there, move that down to there, we come up with this expression, which comes out of an RE dash of 3.68. And I just said before that RE dash equals RE, our emitter resistor, in parallel with that degeneration resistor, R2X. So therefore I can use our parallel resistance equation to rearrange that to derive what R2X needs to be, which turns out to be 6.69 ohms, so I'm going to use 6.8 ohms. So that pretty well, from a stage 2 point of view, has established what that needs to be in terms of a load resistance. We've got our first resistor for the voltage divider bias, we've got that one, we've got our emitter resistor, and we've also got our degeneration. So that stage is now done. Right, so moving on to stage 1. So we said, let me just make sure that's all looking good. So we are saying here that if stage 2 is going to be 15 dB and we're outputting roughly half a watt, what does the input to that stage need to be? And rearranging the formula, it comes out to be 15.8 milliwatts. So my stage number 1 needs to be able to pump into stage number 2 15.8 milliwatts. So same sort of logic. If that's the case, and I'll work on a 30% efficiency, then that power divided by 0.3 comes out at 52.7 milliwatts. So my DC input, so same logic as before, needs to be that power there. So if that's the case, then I can then go 52.7 milliwatts divided by 12 volts, which is the supply voltage, comes out at 4.39 milliamps. So that'll be my quiescent current I'll use for the first stage. Exactly the same logic as we saw for the stage 2. Again, for stage number 1, the load that needs to be presented to the collector is VCC minus VE, all squared divided by 2 times power out. So same sort of thing, plug the numbers back in, and we come out with 3691 ohms. So my RL, which we'll need there for T2, that second transformer between the first and the second stage. I won't go through this, so same logic for working out our emitter resistor. Comes out at 273, so I'll use 270 ohms. Same logic as we've seen before for determining the 2 resistors for the voltage divider biasing. First, the bottom one, so stage 1, 2, so the bottom resistor, 10 times our base current. Comes out at 4.8k, so I'll use 4.7k. That top resistor in the voltage divider biasing for the stage 1, so 12 minus the base voltage, now 11 times of course, comes out at 23k, so I'll use 22k ohms for that. Same again for working out what RE dash is going to be. So let me just go back up to this page. So rearranging that formula we just saw before, if gain is approximately equal to 10 log RL, our load resistance, divided by our emitter effective resistance, or RE dash, that'll work out to be an RE dash of 116.7 ohms, and therefore we can rearrange the parallel resistance formula to equate what R1X, so that degeneration resistor, needs to be. Comes out at 205 ohms, so I'm going to use 200 ohms. And that's effectively that then. So now we've got the biasing for both stage 1 and stage 2, and now we'll just sort of race through and work out what these transformers need to be. It needs to be labelled T3. Right, so T1, the output of that second mixer from the TUF3 is 50 ohms, and that needs to be matched to what Rin is going to be for stage number 1. Rin is R1 in parallel with R2, so that's the voltage, the two resistors for the voltage divider biasing. If I want to use the same notation as before, it's going to be R11 in parallel with R12 in parallel with beta AC multiplied by little re plus re dash. All of these are known, so we'll plug them in. So 22k in parallel with 4.7k, 14.3 comes from our beta AC there, 100 megs divided by 7 equals 14.3. Divided by little re, so 26 divided by our emitter current in milliamps, so 4.39, plus our re dash, which was 116 ohms, which was back up here. It comes out at 1207, so I need to match 50 ohms to 1207, which comes out of a turns ratio of 4.9, and I'm going to use 4 to 20. Knowing that from the IF stages in the antenna amplifier that 4 turns on an FT37-43 at 7 megahertz gives me an inductive reactance which is greater than 5 times, yes it is, yeah, greater than 5 times 50 ohms that that's connected to. So I've sort of just cheated and started looking at 4 turns, 5 turns, 6 turns to work out what it's going to be. So I'll use that's close enough. Right, so T2 is now matching the load that stage 1 wants to see with the input resistance to stage 2. And you'll recall later on when we get down there that stage 1 wanted to see 3691 ohms as a load, and using exactly the same logic as we've seen before, we can now calculate what our Rin is for stage 2. So R21, that's the first resistor of the voltage divider, in parallel with R22, second resistor, again beta AC, little re, so 26 divided by now 138 milliamps, plus re dash, which we calculated before to be 3.68. Comes out at 38.14 ohms. So therefore we can work out our turns ratio, the square root of the two impedances as a ratio, comes out at 9.83. So it's quite high. So straight away we can see there that it's 4 to 39. And that's the reason why I initially tried to have a look at, that's why this was drawn later, at this network here. As it turned out, when I was actually playing around and doing the actual tests, I really couldn't get this to work very well. From a maths point of view, if I was just to bring that page up, I think it's this one here, here it is. So what I was trying to do was using this L network to match 3691 ohms to 38.14, so the load that stage 1 wanted to see with the input to stage 2. And this was the configuration here. So the series inductance was going to be, or reactance more the point, sorry, is R1 times R2 minus R1 squared, noting that you need to have R1 smaller than R2. Comes out at 373 ohms. The parallel reactance is R1 squared plus our series reactance squared divided by our series reactance. Plug those numbers in, you come out at 376, you can read it there, 376.8 ohms. And the Q is square root R2 over R1 minus 1, again comes out at 9.78. Not too worried about the Q because it's reasonably fixed, around that set of 7.1 megahertz. So at this stage I've left it at the 9.78, and we'll see how it works, like I say. Now we know once we've got those two reactances, this one's obviously an inductor, this one's a capacitor, we can then use the formula for capacitive reactance and inductive reactance to then reverse engineer what the capacitance and the inductance needs to be in each case, working on a frequency of 7 megahertz. If that's the case, just rearranging that formula to make the capacitor the subject, comes out at 60.3 picofarads. So I used a 30 puff in parallel with a 30 puff, or it's basically a 40 puff variable trim capacitor. So I did for that one there. And then the inductor itself turned out to be 8.48. That's not microfarads, that should be microhenries. I'll fix that now, I've got time. Microhenries, and for a FT37-43, that's very close to 5 turns. So that's what I did for that, and like I say, it wasn't that good, so in the end I reverted back to a transformer which had 4 to 40, so I just rounded that up. No, sorry, 4 to 39, which is what I used. Right, okay, I might just come back to these numbers here, but in terms of playing around, what's the best way of doing this? I think I might just leave it like that. What I did is initially powered it up with a, okay, I don't know if it makes sense here. What I wanted to do is, I don't know what the input resistance to the FET amplifier was going to be, so I initially just tried a 50 ohm resistor and then worked out what the turns ratio needed to be to transform that 50 ohms back up to what the second stage wanted to see for its load. And you'll recall that the second stage here wanted to see 116 ohms there, so the turns ratio was at 1, 2, 3, 4, 5, 6, 6 to 5 if I recall. 1, 2, 3, 4, oh maybe it's 4. Right, so that's what I initially set this to be, and then started to play around with throwing an input in. So if we can try and pick up both of these, and I apologise, this sounds like a bit of a ramble, but yeah. You know what I'm like here, I just sort of just play around and talk, so it is what it is, I'm afraid. So let's just key it up. So at the moment we've got 60 millivolts RMS going in, and we're getting 3 volts on the output. Could increase that slightly more and get up to 5 volts, so that's 5.23 volts RMS. That's 4.85. Bit of non-linearity there. But that's effectively just sitting on now half a watt at 5 volts RMS. And if I come back down to say at 3.51, then we get a lot better linearity. Of course, on the output of that second stage is going to be a low pass filter anyway, but I want to try and keep these stages as linear as I can. Anyway, so what I then decided to do was go, right, okay, well having said that, I tried then different values of resistance on the output of that transformer. I left the transformer turns ratio where it was, and I played around with different values from 33 ohms through to 220 ohms. So that's what that column there is. This column here is volts RMS that was measured across that, and then given that volts RMS, so that voltage squared divided by that resistance will give me the power that's being dissipated or transferred to that particular resistance. And as you'll see here, that at the two extremes we're starting to drop off. So if I was to graph this, we have a definite peak at 56 milliwatts occurring at 150 ohms. If I go any higher than that, sure, I get more voltage, but my power actually being dissipated in there starts to drop off. And same when I go less than 150 ohms, you can see here it starts to drop off and gradually gets further and further down. I didn't actually measure 82, but you can see the trend there. So as we're getting higher up, increases in power, peaks at 56 and then starts to drop off again. So at the moment, left in place is 150 ohms load resistor. So Right, so I know the input is was 56. No, so the input, sorry, power. Sorry, I'm starting to ramble here again. I didn't write my notes down clear enough. The input power at the moment is 0.072 milliwatts. I'm outputting 56 milliwatts. So just ignore the second part because it's the same. 56 divided by 0.072 log times 10 will give me a 29 dB power gain across the whole amplifier, which is pretty close to my 30 dB that I was after in the first place, and that's maintaining the linearity which I wanted for the SSB transmitter. I hope that made sense. I have a funny feeling it didn't, and I apologize for that. I don't have time to re-record this. I'll just leave this as it is. So that's where we're at. What else I want to cover off on? Yeah, so I'm pretty happy with that. What else worth covering? So I think this stage of the game, when Christmas is over and I can get back in the shack again, will be a matter of building up that FET power amplifier. I don't know if that's going to be based on an IRF 510 or another device I got lying around. We'll just have to see what goes on there. And then what I'll probably do, once that FET second stage is in place, I'll then play around with this turns ratio here to again look for the maximum power transfer between effectively stage 2 here and that particular power amplifier, and hopefully it'll go from there. So I'm aiming overall for 5 watts out. Around there would be quite nice. You know, I'm not after huge amounts of power, and given the kind of the battery pack that I've got anyway, I can't produce too much more than that as it is. Anyway, so I'm keen to sort of hear back to see if that was an appropriate way of approaching the design for this particular this driver for the PA. Like I say, that transformer there worked out to be a whole lot more effective than that matching network. I've tried the matching network before and it didn't work for me, so I'm clearly doing something wrong, and that may be something which I need to dedicate a good amount of time to, just to really understand how that works, because it is a common way of transforming two impedances, albeit with the transformer here it's a lot, well, certainly with the FT range it's broadband, whereas with that particular matching network with a Q of, what was it, 9.9 roughly, the matching would certainly drop off the further away I got away from that 7 megahertz drive or design frequency. Noting that in EMRFD and SSDRA, those two textbooks, they say that the Q for that particular matching network, the inductor and the capacitance, is not necessarily a good drive or indication of its bandwidth. But again, I got poor performance, so I just took it out and replaced it back with the transformer with the 39 turns. Okie doke. Well, I'm going to say again, as per the last video, Merry Christmas and Happy New Year, everybody. I'll be back in the shack after Christmas and start to work on that FET power amplifier, and we'll see where we go. I don't have to rebuild this. I made that in a circuit board size that was suitable to fit straight into the chassis that I've got so far. Anyway, 73s, and we will see you very shortly.